on this. Okay, this is a shout out to those who are taking the lab. I'm going to be sending out an email today. The lab final, if you're actually in the live class and have Top Hat, you can take the lab final on Top Hat. So it'll be much easier than doing the Zoom proctoring. If you do not want to do it on Top Hat, or you want to do you can also sign up for the Zoom proctoring. It's just we can only have about 25 people per screen, and so we'll have to kind of stage it a little bit, but you will be able to take it anytime on that Wednesday, well, between 12:30 and 6:30, depending on your exam schedule, which lab you're in. So I will be sending out an email for that, and so hopefully that will make things a little bit easier. Okay, I gotta remember to send that out today. Okay, let's get back on track. We were talking about carboxylic acids and carboxylic acid derivatives. And so what we found out was that carboxylic acids are kind of cool. They're the most oxidized. They take priority when we're naming them. But then the derivatives we have, which I believe is this chapter, yeah, is we can see that the derivatives are all related to the idea that we can put water in or remove water to get these derivatives with other functional groups, okay? And we've talked about how we name them and what lactones are and what lactams are, which are the cyclic versions of the ester and the amide collectively, okay? But now let's talk about the other reactions that these carboxylic acid functional groups do. So I'm going to go ahead and share my screen, and let's see if that shows up. All right, there we go. All right, can you see my screen?
Yes.
All right, so we were talking about these cyclic materials and how they're used in a lot of biological systems. Okay, remember when we were talking about the carbonyl compounds and we looked at aldehydes and ketones, we were attacking that partially positive carbon with a nucleophile, okay? So in the case of having carboxylic acid derivatives, we can do the same thing. However, in the case of the aldehyde and the ketone, we would have a hydrogen negative or a carbon negative as a leaving group. Those are very bad leaving groups. So they would be addition products when we attack with a nucleophile. When we have things that can be good leaving groups, we actually get what we call nucleophilic acyl substitution, meaning we're going to substitute and regenerate that double bond with oxygen. Okay, so this is different. When we had aldehydes and ketones, we hit them with the nucleophile and we turned it into alcohols. Here we regenerate the carbonyl, and so we can change the functionality from one group to the other by kicking out a leaving group and reforming that carbonyl. So this substitution reaction happens with all of the different substituents, and it's all based on the basicity of the leaving group. Okay. So the general reaction that happens is a nucleophile will come in, it'll form that tetrahedral intermediate state, and then the weakest base will leave, regenerating our carbonyl. And so we have to think about what is the weakest base. Obviously, neutral molecules like water, alcohols, and ammonia can serve as nucleophiles, but we want to look at the actual negative group that's leaving as our leaving group. And if we remember from our basicity and our acidity is, the stronger the acid was, the weaker the base is. So that means when a halogen leaves, it is a really good leaving group because it's a really, really weak base, okay? And so our conjugate acid here is HCl, and that makes it a strong acid, which makes it a weak base, which makes it a great leaving group. Over here, this is the acetate ion, which means its conjugate base is acetic acid, which makes it a pretty good leaving group. And then we have alkoxide right here, which had the alcohol as a pKa of 16, which is okay. It's not as good as acetic acid, but it's pretty good. And then our last one is the amide leaving functionality. And it actually has the The conjugate acid, those pKa's are closer to 20. So that's the highest. So this is the least acidic material, which makes it the most basic material and makes it the hardest group to leave. So let's look at this series again, okay? As the basicity increases, its ability to leave decreases, okay? So we want to think of things like this chloride ion, because of its low basicity, is easy to leave. In fact, it reacts spontaneously with water and air, okay? The acetate group is a good leaving group. Again, it's an anhydride, it's a spontaneous leaving group. The ester, we can get to leave by hitting it with another nucleophile. In the amide, it's going to be really hard to get rid of, but we can get rid of if we hit it with a really, really strong nucleophile. Okay. So let's continue that argument about what happens here. If the halide is the best leaving group, that means it's going to be the most reactive toward this nucleophilic substitution. And if the amide is has the worst leaving group, that nitrogen anion is the worst leaving group, it should be the hardest thing to do substitution on, okay? Which means that we have the acid halide is more reactive than the acid anhydride, and the acid anhydride is more reactive than the ester. And the ester and the carboxylic acid are about the same because the leaving group would have been hydroxide, okay? Alkoxide and hydroxide are about the same base strength, so they're approximately even. And then this amide anion is the strongest base of the set and is the worst leaving group. Therefore, it's going to be the slowest or hardest to react. Okay, so that's why we get these substitution reactions, and that's why we have the different reactivity with the different functional groups we have with these carboxylic acids. Okay, so let's talk about the most reactive one, the acid chloride. The acid chloride will spontaneously hydrolyze anywhere it comes near water, and it'll generate HCl because the chloride is the leaving group, and the water is the nucleophile. It's going to come in, form our tetrahedral intermediate, and then it kicks out the weakest base, which is the chloride ion, and it has to deprotonate the water, and that's where the hydrogen comes from. Okay, so the smaller the molecular weight, the more rapidly they react because they are more likely to be soluble in water. As they get bigger and bigger, they're going to be less and less soluble in water, and they react more slowly. Okay. So likewise, the anhydride is just two carboxylic acids we removed water from. So the reverse reaction also goes through. We have low molecular weight anhydrides react very readily with water to give 2 equivalents of carboxylic acid. The higher ones take a little bit slower, but again, because they're less soluble in water. So the same thing that's going to happen is you have water acting as a nucleophile. It's going to give us our tetrahedral intermediate, and then the weakest base, in this case, the acetate ion, is going to leave, and then it transfers the proton from the hydronium back to the carboxylic acid, giving us our final product, our carboxylic acid. Okay, so questions on that? Okay, so if that's what's happening there, let's look at the esters. Okay, esters are a little harder because they hydrolyze slowly without catalysts because the leaving group is about the same nucleophilic strength as the water coming in, okay? The hydrolysis is more rapid when heating with either acid or base. So we can catalyze the reaction with acid or base to make it go faster, okay? Now, if you are hydrolyzing in acid, this is the reverse of the Fischer esterification. In the Fischer esterification, we made the carboxylic acid ester using an acid catalyst. In this, we're reversing that reaction by adding more water to the system than alcohol, and we can drive the equilibrium in the other direction. Okay. The key step in this mechanism happens to be that tetrahedral intermediate. That tetrahedral intermediate is going to tell us which group is going to leave because which group is going to be the weaker base. All right, so let's look at that intermediate, okay? So the first thing that's going to happen is water is going to act like a nucleophile. And if it just reacts with this right here, oops, yeah. If it just reacts like that right there and doesn't protonate the carbonyl, that just can reverse back and forth, back and forth. However, if we protonate the carbonyl first, it makes it easier to form our tetrahedral center. So by protonating that carbonyl first, when we get to our tetrahedral center here, only the water coming in has a positive charge. Okay. So now we have things that can happen. We can either lose the water and it'll go back to that original protonated carbonyl compound, or we can move forward and transfer that proton to the alcohol and make the oxonium cation, the alcoholic cation here. And once it does that, that makes the alcohol a good leaving group now. So we can actually kick in the electrons to regenerate our carbonyl, and then that kicks out our electrons to form our neutral leaving group. So notice the alcohol that's leaving is neutral, and that we used the water as the solvent to take away the proton, regenerating our hydronium ion. Okay. So we used a hydronium ion to protonate it in the beginning, which gave us this tetrahedral intermediate, which allowed us to transfer the proton to the alcohol to make a neutral leaving group and our carboxylic acid. Okay, so what's going to drive this reaction? Okay, before, when we were making the alcohol, you used a large excess of the alcohol, or you removed the water from the reaction to drive it to make the ester. In this case, we just use a large amount of water with an acid catalyst, and it'll drive the reaction back to the carboxylic acid and the alcohol. Questions about the acid catalyzed hydrolysis of esters. So we regenerate our acid, so it's just catalytic, and we can keep going and going and going. As long as we have water or an excess of water, it'll continue to move toward the carboxylic acid and the alcohol. Okay. However, if we use base to catalyze the system, it actually doesn't catalyze the system. We have to actually use a whole equivalent of the base, and I'll show you why. So it's really, if we hydrolyze an ester in an aqueous base, it's called saponification, okay? And we have to use an entire equivalent of hydroxide, because when we form the reaction, it actually creates the carboxylic acid salt, okay? And so we have to use an entire equivalent of base to do it. Okay? So in the case of this, the base promoted ester hydrolysis also involves that tetrahedral center, but then again collapses down to give us our carbonyl back. Okay. So let's look at the steps on that. So in this, instead of something coming in as a weak nucleophile, we actually have hydroxide in the system. So hydroxide is actually a really good nucleophile and will come in and attack at our carbonyl compound and generate these electrons, kick up and generate our negative charge here. Okay. So now we form our tetrahedral center. Okay. But now we have to have something leave, okay, to regenerate our sp2 hybridized carbon. And so we have a competition between, it can lose the hydroxide, but that just takes us back to the original ester. However, if we lose the alkoxide, lose the negatively charged alcohol, we now have hydrolyzed off our ester and we have our carboxylic acid. Okay, and because the sodium hydroxide is such a strong acid, it's going to deprotonate that carboxylic acid we just made and turn it into the anion here. And then, I'm sorry, because the methoxide is the stronger base between the carboxylic acid and the alcohol, the methoxide is going to deprotonate the carboxylic acid, generating neutral alcohol and the salt of the carboxylic acid. Okay, so this is the reason that counterbalancing ion, that sodium or that potassium, it actually makes the salt with this. And that's why it takes an entire equivalent of the base to using base to remove that alcohol from the ester, to hydrolyze that ester. Okay. So does that make sense? In the other one, you actually regenerated hydronium, so you could use just a little bit and catalyze it. Here, we actually are using that sodium to make the salt, or potassium to make the salt of the carboxylic acid. Okay. Okay. So there's two major differences between the acid catalyzed or base promoted. One is the acid catalyzed just takes a drop and a bunch of water, okay? And it'll create equal moles amount of the ester or the and the carboxylic acid. Okay. In the base promoted, we have to use an entire equivalent of base, and it's going to generate amount of the carboxylic acid salt and the alcohol. Okay. In the case of the acid-base system, it is reversible because you have the carboxylic acid that can now be attacked by the alcohol as the nucleophile, and it can go back reaction to give you the ester. But in the base promoted, because you're ending up with the carboxylate ion, it itself is not susceptible to nucleophilic attack, and it's a poor nucleophile, so it doesn't attack other things, and therefore the reaction stops. All right, so questions on the two ways to hydrolyze an ester. Okay. Acid catalyzed or base promoted or equimolar base to ester. Okay, so amides now become harder, okay, because the leaving group could be a nitrogen anion. That would be very, very difficult because it's a very strong base. So most of the time when we do the amide hydrolysis, we typically use acid, but we have to use more than one equivalent of acid, okay? So it's at least one equivalent of acid, usually a little bit more, to make this go forward. And the reason we do that is we are protonating the nitrogen so it never leaves as the anion, okay? So in this case here, we have to have at least one equivalent of water. We need to have at least one equivalent of acid and one equivalent of our amide, and it'll drive it to our carboxylic acid and some kind of nitrogen or ammonium salt. Okay, so let's look at the mechanism again. Okay, oh no, let's talk about aqueous base. When we hydrolyze amides, just like when we hydrolyzed esters, it takes an entire equivalent of base to be able to do that because you're forming the carboxylate salt and the unprotonated amine. Okay. So in the case of amides, you have to use an entire equivalent of acid or an entire equivalent of base. With the esters, catalytic acid, entire equivalent of base. Okay. So let's look at those reactions right there. We have the acid chloride reacting with water, and it's not in equilibrium. It goes immediately to the carboxylic acid and the HCl. Okay. When we have the anhydride, it's not in equilibrium. It just goes to generating two equivalents of carboxylic acid. Okay. When we have the ester and we use base called saponification, it's not in equilibrium, and it just drives everything to the carboxylic acid salt and the alcohol. When we have acid catalyzed, it is in equilibrium. So we have to have excess water or remove the alcohol to drive the reaction to completion. There's always a little bit of back reaction in that. Okay. When we hydrolyze the amides, neither of these reactions are in equilibrium because once we drive the base mediated hydrolysis, we end up with the carboxylate salt, which is no longer attacked by nucleophiles. In the case of the acid catalyzed system, the amine is now no longer nucleophilic because it's the quaternary ammonium salt, or the ammonium salt of the system. And this is no longer reactive. Okay. So the only one we have to worry about reversibility is the acid catalyzed system, but all we have to do is add extra water and we can drive it to the carboxylic acid. All right, questions on that? And in addition to being in this order, it's the order of reactivity too. The acid chloride is much more reactive than the anhydride, which is more reactive than the ester, which is more reactive than the amide. Okay. So do they just react with water? Well, no, they would react with anything that has a nucleophilic center on them, right? So alcohols can act as a nucleophile. So if we take an alcohol and react it as a nucleophile, we're going to get that tetrahedral center, but then we're going to lose the chloride ion as a weak base. In that process, we can convert our acid chloride to the ester, and then with a little bit of acid behind. So again, we're doing the same mechanism. We're making that tetrahedral center, and then the weakest base is leaving. So we can also do that with anhydrides because the leaving group is a carboxylic acid that is a weaker base than the ethanol. Remember, the conjugate base of the acetic acid is what we're talking about here. And therefore, it reacts with one equivalent of alcohol, reacts with one equivalent of the anhydride to create one equivalent of the ester. That's the one that made the tetrahedral center, and then it kicked out that one equivalent of the carboxylic acid. So only one side of that anhydride creates the ester. The other side of that anhydride creates a carboxylic acid. Okay. And we actually use that reaction to create aspirin. Aspirin is acetylsalicylic acid. And what they do is they have a carboxylic acid on a benzene ring with an alcohol next to it. It's 2-hydroxybenzoic acid. And when you react it with acetic anhydride, which is the anhydride made from acetic acid, we get the acetyl ester right here. And that is what makes it a little less water soluble and actually makes it easier to use as a pharmaceutical material. So a salicylic acid actually is kind of hard on your stomach. And they figured out by taking away that hydroxide, by making the acetyl group there, it's actually easier on your stomach and easier for you to ingest into your body. Questions on making esters from anhydrides? You're only going to make one equivalent of ester and one equivalent of carboxylic acid. All right. So, okay, we had acid chlorides, and they react with alcohols to make HCl and an ester. We had an anhydride, they make an ester and a carboxylic acid. Well, do esters react with alcohols? Yes, they do. They react with alcohols in a way in which they turn one ester into another ester. When we turn one ester into another ester, that's called trans-esterification. We're converting one ester to another ester. And this is typically done where it's acid catalyzed, and we can take off one group and add another group. It works best if you have something that has a low boiling alcohol and something that has a high boiling alcohol, so you can drive the reaction to completion. Because as long as you have alcohol in there, it's a reversible reaction. So let's look at this reaction here. In this case here, we have two equivalents of this methyl benzoate. So that means the alcohol component of our ester is methanol. Okay? And that boils around 56 degrees. Then if we take it and have a higher boiling one, ethylene glycol, which boils at like 200 degrees C, and we add a drop of acid, we can slowly use our alcohol as our nucleophile, and it's going to come in here and slowly displace the methanol. As it's displacing that methanol can boil out of the reaction mixture and drive the mechanism to completion, drive the product to completion. In this case, because we have two alcohols, we have ester on one side of it and an ester on the other side of it. And this just happens to be the diester of ethylene glycol. Okay. So again, that acid catalyzed hydrolysis or trans-esterification is a reversible reaction, but we can force it to go by adding a whole bunch of one alcohol or removing one of the alcohols. Okay, and amides don't react with alcohols, right? Because the thing leaving would be much more basic than the thing we're attacking it with. So there's actually no reaction with the alcohol when we have amides. Okay, the ammonia is a much, much better nucleophile than the alcohol, and therefore nothing happens. All right, questions on that? So that's a lot of reactions and things that happen and stuff, right? Well, let's take those same reagents and attack it with a really good nucleophile. Okay? So in the case of acid halides, they can react with any nitrogen as long as it has a hydrogen on it. So that means ammonia with three hydrogens, a primary amine with 2 hydrogens, or a secondary amine with 1 hydrogen. Tertiary amines will just form salts with them. It doesn't actually react, okay? But you have to have 2 moles, 2 equivalents of the amine. Why? Because with the acid halide, you're going to try to have HCl leave. You're going to have an acid leave. Well, the ammonia is not only a good nucleophile, it's also a good base. So the first equivalent is going to be used to make the amide. The second equivalent is going to be used to neutralizing the HCl byproduct. Okay, so we have to keep that in mind. All right, does that make sense? Ammonia is a really good nucleophile, but you have to have at least 1 hydrogen because you have to kick out an HCl. And then acid anhydrides also react with nitrogen compounds as long as they have at least 1 hydrogen. But just like before, you have to have 2 equivalents because the first equivalent is going to make your amide. And then when we make our amide, that's going to create a carboxylic acid. The carboxylic acid is then going to react with the basic part of the ammonia to create a carboxylic acid salt. So again, we have to have 2 equivalents of the amine to make the reaction go to completion. And we're going to end up with a salt and an amide. Actually, the salt is on the right and the amide's on the left. Okay, so we were able to take a really good nucleophile and displace a chloride. We were able to take a really good nucleophile and displace a carboxylic acid. We can do that again by displacing that alcohol in an ester, okay? The ammonia or the amines are much better nucleophiles than the alcohol being formed. So they do react to form the product here. So we can take any amine as long as it has at least 1 hydrogen, use it as a nucleophile. And notice the proton ends up going to protonate the alcohol. That's where that other hydrogen went. And so we have a neutral acetamide and a neutral alcohol. So in this case, it only takes 1 equivalent because we're kicking out a neutral alcohol as our system. Okay. Now, once you have that amide on there, it does not react with any other nitrogen compounds. They're just not a driving force for it. The one that's on there is stuck there. You can't react them further. So amides don't react with ammonia, and they didn't react with alcohols either. So the summation of that is we have to have 2 equivalents if we generate acid. So that's HCl in the form of the acid chloride and acetic acid or carboxylic acid in the form of a anhydride. In esters, we only need 1 equivalent because it generates neutral water. And amides don't react with other amines. Okay. So this entire chapter is now summed up in this chart. Okay. So the way to read this chart is we're going to start with carboxylic acid, okay? And we're going to start with that carboxylic acid because that was chapter 13. That's where we start. And the first thing we learned is we could make the acid halide by reacting it with thionyl chloride. Okay? And we learned that thionyl chloride was very reactive. It reacts with water, it reacts with everything. Okay? In fact, it's the most reactive species, and you can make every other carboxylic acid derivative from it. If you want to make the anhydride here, we didn't show that reaction, but you actually just use a carboxylic acid salt. If you want to make the ester, you just react it with the alcohol. You want to make it the amide, you react it with an amine. And if you want to react it with a water and a base, you end up with this carboxylic acid salt right here, the carboxylate ion. Now, if you have the anhydride, you cannot make the acid chloride. It's more reactive. But you can react it with an alcohol to make an ester, or react it with an amine to make an amide, or react it with basic water and get to the carboxylate salt. Okay. Just like that, your ester, you can't go back up. You can't make an anhydride or an acid chloride. That doesn't work. But you can make an amine out of it, or you can hydrolyze it to make the carboxylic acid salt. The only thing an amide does is hydrolyze to make the carboxylic acid salt. Right here. Once you have your carboxylic acid salt, you just have to add acid to bring it back to the carboxylic acid. You can start the whole cycle again. Okay. What do we think about carboxylic acid derivatives?
That chart is super helpful.
Yeah, do you see the thing that's it's reactivity from top to bottom and conversion from top to bottom? So really, I think sums up the entire chapter quite well. Okay. So when we looked at aldehydes and ketones, we saw that we could do reactions on that carbonyl using Grignard reagents, right? Our Grignard reagents, that magnesium carbon bond where the carbon is mostly negative. And we said that carboxylic acids are in that class of compounds that have a carbonyl, okay? So what if we have a reaction with a Grignard? Well, it turns out if you just have one Grignard, what's going to happen is it's going to remove the alcohol of the ester, and then it's going to reform the carbonyl because the alkoxide is the weaker base. So if it reforms that carbonyl, it can still react with the Grignard and react to form another. So when you react esters with the Grignard reagent, you use two equivalents, okay? So it's going to use one equivalent to displace whatever your alcohol was, and then it's going to use the second equivalent to generate our substituted product, not our, our addition product, not our substitute product. Notice we make an alcohol from this. Okay, let's look at this first example here. In this first example, we have a methyl formate. We have the methyl here as the alcohol and formic acid as the, so we have a hydrogen here, okay? So the first thing that's going to happen is we're going to displace this and put an R group on there and get to an aldehyde, but it's not going to stop there. We're going to take our second one and put another R group on here. And what that's going to do is going to put a charge up here to give us our salt. And then when we add acid to it, we're going to end up with a secondary alcohol, okay? You cannot stop at the aldehyde. You have to put two equivalents in and get to your secondary alcohol. Does not stop at the aldehyde. If you have an ester of any other type, you end up with a tertiary alcohol. The only reason you have a secondary alcohol is because we have a hydrogen hooked to the carbonyl, and this is the carbon that was the carbonyl. If you have any other group there, you're going to displace your alcohol group, and whatever Grignard reagent you have are going to be those two other positions on our tertiary alcohol. Okay. And you have to have that acid and water to break up that magnesium complex to give us our free alcohol. Questions on that? So this isn't a substitution reaction. We're actually adding 2 equivalents to that Grignard to turn it into an sp3 hybridized tetrahedral center. Okay, so let's look at the details here. Okay, remember we have a partially negative carbon here. This is the partially positive magnesium. Okay, it's a polar bond, but it's still a covalent bond. Okay, so we can take the electrons from that polar covalent bond and attack as a nucleophile to the carbonyl, generating our first salt here. Okay, now we can wait around for a little while, or if we kick the electrons in from this salt to form a carbonyl compound, we can kick out methoxide right here. That's the weaker base compared with the Grignard reagent to the methoxide. That's the weaker base. And in this case, we had an R group on here, so we generated a ketone. Okay. But that ketone is reactive toward nucleophilic attack. So that's where the second Grignard comes in. The second Grignard comes in, and the electrons that are between the carbon and the magnesium act as the nucleophile and attack, generating our negative charge up here and our magnesium salt and our tetrahedral center. Notice we would have to kick out a carbon with a negative charge to have one of these groups leave. That's way too strong a base. That's why we have addition products with aldehydes and ketones, because the hydrogen minus and the carbon minus are bad leaving groups. But we can have substitution products on the other carboxylic acids where we're losing chloride, acetate, alcohol, etc. Okay. And then, of course, when we protonate that, it turns into our neutral alcohol. All right, does that mechanism make sense? So I thought we had another mechanism where we had something else reform a carbonyl and then it reacted again. So, okay, so let's go back to a reduction, right? When we talked about reductions, we said that we could use sodium borohydride or lithium aluminum hydride to reduce certain things. And the sodium borohydride is less reactive and therefore only reduces aldehydes and ketones to their respective alcohols. For esters, because we have that extra oxygen, it's harder to react, and so we must use lithium aluminum hydride. Okay, regular sodium borohydride will not reduce down the carbonyl. Okay, notice in addition, we're using that, we're going to take that ester, we're reducing off the alcohol as well. So whenever we have a reduction of an ester, we end up with 2 different alcohols. We end up with the alcohol generated from the side that was the carboxylic acid here, and we end up with the alcohol that was what we would call the alcohol on the ester. All right, so we're doing that because we're adding hydrogen across this bond and hydrogen across that bond and generating our thing. Notice in this case, we always get a primary alcohol because the alcohol, the R group from the ester leaves, and we end up putting 2 hydrogens on the carbon with the carbonyl. Okay. So sodium borohydride is not strong enough to do that, but we can use that to our advantage. What if we had an ester on one side and a ketone on the other? We can selectively reduce the aldehyde or ketone and not touch the ester. Okay. Now, what if we had an amide? Okay, let's see. If we had an amide, in the case of the ester, the alkoxide came off because it was a pretty good leaving group. But in the amide, what happens is it reduces down the carbonyl, but keeps the carbon-nitrogen bond. Okay, and again, we have to use lithium aluminum hydride. It's the only one strong enough to do the carboxylic acid derivatives, the esters and the amide. So if we took something like this octanamide here, and we used lithium aluminum hydride, it's going to reduce this down once, and then it's going to reduce off the oxygen. Notice our final product has the oxygen removed. Only the nitrogen stays, okay? In the case of the ester, we ended up with an alcohol, okay? In the case of the amides, we end up with an amine, okay? And we'll end up with whatever amine we had before. If we had a secondary amide, we're going to end up with a secondary amine. If we have a tertiary amide, we're going to end up with a tertiary amine. Because the only thing that goes away is this is reduced off as water, and we end up with the two new hydrogens where that carbonyl was. All right, questions on that? Okay, so this actually gives us an interesting opportunity here. Remember when we tried to use ammonia as a nucleophile, and we had an alkyl halide, and we said that it was very hard to get a mono-substituted amine or a primary amine because when we reacted the ammonia with an alkyl halide, it was still nucleophilic. And we react again and again and again until you end up with a mixture of primary, secondary, tertiary, or quaternary. So notice we end up with whatever type of amine, whatever type of amide we started with. If we started with a primary amide, we get a primary amine. We started with a secondary. So it's a very clean way of getting to the exact primary, secondary amine or tertiary amine that you want. Okay. So let's interconvert through all these functional groups and talk about the reagents we would need to do so. Okay. So if we started with just this, and this is phenylacetic acid, it's got a phenyl group here, and this part right here is acetic acid, and it's got a phenyl group on it, so it's phenylacetic acid. Okay. And we took it and we reacted with thionyl chloride, we're going to end up with our acid chloride, which we can make a lot of other things from, right? But we could also take our phenylacetic acid and we could reduce it down with lithium aluminum hydride. If we did that, we'd end up with a primary alcohol. Or we could take it and react it with catalytic acid and an alcohol right here, and we're going to turn it into the ester. But we could make the ester from the acid chloride too. All we have to do is add a little alcohol. And we know that we just learned that we can reduce our ester using lithium aluminum hydride and get to the primary alcohol again. Let's say we didn't want the primary alcohol. We wanted to get an amide. Well, let's go ahead and convert our ester to an amide, and then we can convert our amide to an amine. Okay, so one starting material, we've gone through all but the anhydrides of the carboxylic acid derivatives to get multiple unique products: acid chloride, ester, amide, amine, or alcohol. All right, questions? Okay, let's see. I think that's the end of the chapter. So that's the summation of that. And this chart and the one with all the different carboxylic acid derivatives interconversions is really the summation of all the reactions in this chapter. Okay. So let's take a breath, turn a page in the notebook, get ready to do chapter 15. We're going to do the last chapter in which we're going to talk about the carbonyl compound. Okay. But we're going to use it in a completely new way. Okay. So in chapter 15, we're going to talk about how the carbonyl, its partially positive nature, can make the hydrogens on adjacent carbons more or less acidic, meaning we can do reactions on those alpha carbons, those carbons won over from our carbonyl. So let's talk about alpha carbons and beta carbons. Now, obviously, the alpha carbons are going to be the carbons next to the carbonyl, and the alpha hydrogens are going to be the hydrogens on those alpha carbons. Okay, so if you think about it, ketones have at least alpha carbons on either side, and therefore usually have alpha hydrogens. Okay. Now, it turns out the alpha hydrogens on aldehydes, ketones, and esters are more acidic than if they were alkanes or alkenes, but less acidic than the hydroxyl hydrogens. So it's less acidic than water, but it's more acidic than alkanes or alkenes. So somewhere on that basicity chart, we have these alpha hydrogens lie. Okay. So let's look at that and try to figure out why. Why would those be more acidic? Well, let's see, we probably have some kind of resonance effect or inductive effect. So the first thing we have is that carbonyl compound is electron withdrawing because it has a partially positive charge on carbon. So it's going to be pulling some of the electron density away from it. And remember, that's creating an easier way to form a negative charge because we're pulling electron density away. Anytime it makes it easier to form a negative charge, the hydrogen becomes more acidic. So, and we can help this using a resonance stabilized material where we're trying to stabilize the charge on both the carbon and on the carbonyl oxygen. So let's see what that looks like. Let's pull this up. Okay. So the fact that we are withdrawing electrons in this direction toward the carbonyl is helping it become more acidic, okay, because we have less of a negative charge to stabilize. But we have a negative charge and we have these electrons up here to play with. So what we can do is if we pull off this proton with a base, these electrons that are formed here can kick in here and form a double bond and kick up here to give us a negative charge on oxygen. We've done negative charges on oxygen quite a bit because it's a more electronegative atom, right? So now we have this resonance stabilized system to where we have a double bond, which kind of looks like an enol, right? If it was had a hydrogen here, it'd be called an enol. And that's why we call it an enolate. It's the salt of an enol. It's the enolate ion. And it spends a lot of its time here, but when it spends its time here, it can act as a nucleophile, okay? The oxygen's not as nucleophilic as the carbon is, and it will react like a nucleophile. Okay. So do we see why that hydrogen, that alpha hydrogen, is more acidic than if it were just a hydrocarbon? If it was just a hydrocarbon, right here, and we tried to pull it off and put an anion here, that anion would stay on that carbon. But because we have the ability for these electrons to kick in here and these electrons to kick out here and have a negative charge, it stabilizes that negative charge and makes it more acidic. Okay. So if you're convinced that alpha hydrogens are more acidic because of the presence of a carbonyl compound, then we can say, what if you have more than one carbonyl compound? How does that affect the acidity? So let's start with what things we know they are, quote, acidic, but they are very poorly acidic. Our alkanes and our alkenes right here. So our pKa of the alkanes is 50 to 60. Our alkenes are 45. And then our most acidic hydrocarbon is our alkyne. However, by putting that electron in drawing group and being able to stabilize that charge on an oxygen, it is now more acidic. Okay. So let's look at this group here. If we look here, we have an ester and a carbonyl, and this alpha hydrogen has a pKa of 22. Okay. So it's more acidic than an alkyne, but it's still not that acidic. Okay. If we take the electron donating of this alcohol group of the ester away and just put a carbon there, turn it into a ketone, it becomes more acidic. So that means that this oxygen is donating some electron density to the carbonyl, making this hydrogen less acidic than if it wasn't there. So, but again, some of the time the negative charge is on carbon and some of it's on oxygen. So alcohols and water are just more acidic than those two enites. However, what if we put two carbonyls on an alpha carbon? What happens? Now we have electronic drawing in this direction and electronic drawing in this direction. It becomes more acidic. So by putting a CH2 between two esters, so we have esters here, it becomes more acidic. But those oxygens in the esters can donate electron density to the carbonyl too, so they're less inductively withdrawing. So let's remove one of the esters and put a carbon there. It becomes more acidic. Okay, so anytime we can withdraw, the more electron density we can withdraw from that center alpha carbon, the more acidic the alpha hydrogen becomes. Okay. Now we move up to phenol. Remember, phenol is more acidic than regular alcohol because we can distribute the charge over the ring. That's why it was more acidic. Okay, let's take away this last donating group and turn it into a carbon. It's the most acidic of the set. It's even more acidic than phenol. It's approaching the acidity of the carboxylic acids at 5. Do we see why they're becoming more acidic? Because the carbonyls are being able to pull more and more electron density, the less electronegative atoms are nearby, and that hydrogen is making it easier and easier to leave because there's less and less of a negative charge. Okay, so when we started with just one ester, and we went to a ketone, and then we had two esters, an ester and a ketone, and two ketones, getting more and more acidic as we got rid of those oxygens in the system. Okay, so let's talk about the ion itself. Okay, once we form that ion, we can then use it as a nucleophile. Okay, so, but we can either form it by driving it to completion and holding it there, or we can hold it with an equilibrium. Okay, so let's look at the first one here. Let's look at this ketone right here. It has a pKa that's higher than that of this diketone, okay, because it only has one electronic drawing group next to this alpha hydrogen. This has two electronic drawing groups next to that alpha hydrogen. So we have to use a very strong base to form our enolate ion. And that enolate ion is stabilized by our anion here. So, and the reason it's driving it is that this sodium amide is a stronger base than this. And so we're going from the stronger acid to the weaker acid, and the stronger base to the weaker base. Okay. pK of 20, pK of 38. We're going from the stronger acid to the weaker acid, stronger base to the weaker base. So that's our driving force here. Okay. However, if that proton is more acidic, we can use a weaker base. This base is weaker than this base, but this acid is stronger than that acid, which means we can use a less strength of a base and still go to our enolate ion and be counterbalancing weaker acid, which is going to turn into water. So that means for a ketone, we have to use the very strong base sodium amide. But once we get two carbonyls on there, we can use weaker bases like alkoxide ion and sodium hydroxide. Okay, are we convinced that alpha hydrogens are acidic now? And we can remove them with bases? But the base you choose has to be associated with the basicity of the thing. All right, so why do we care? Well, we care because if we have an enolate ion, it can react as a nucleophile to create a new carbon-carbon bond. Remember, the first carbon-carbon bond we created was with that Grignard reagent, and then if we deprotonate the alkyne, we can make another carbon-carbon bond. This is a different way to make carbon-carbon bonds, but they're more functionalized systems because you have to use your enolate to attack carbonyl compounds to create addition products. Okay, so let's look at that reaction. Okay, so we have the negative charge partially here, but a lot of the times it's here. When it's here and it acts like a nucleophile, it's going to create a new carbon-carbon bond. And if you blow this up real strong here, we see that this is the new bond here. This is the new bond. It's these electrons are coming in here to create that new bond. And it's a carbon-carbon bond. So we have no good leaving groups. And so it's done. It just does the addition. Okay. So if we have a ketone, it does an addition product and creates the carbonyl that was on the enolate is still there, but the carbonyl that was on the thing that being attacked is now turned into an alcohol. But if we don't have a ketone, we have something with a good leaving group like an ester, we can actually regenerate that carbonyl and do an acyl substitution. Okay, we're doing a carbonyl addition when we can't have a good leaving group. We do an acyl substitution when we do have a. So let's have our enolate form here, and it'll kick in here and give us our intermediate, which is tetrahedral. However, our electrons can kick in, regenerating our carbonyl and kicking out alkoxide. And therefore, we'll end up with a new product. Notice this is a cool product. We have a ketone alcohol for this product, and we have a diketone for this product. You know, we didn't do that with the other ones. We just made longer hydrocarbon chains. We're actually making very functionalized molecules using these enolate reactions. Now, depending on what substrate you're attacking with your enolate, it changes the name of the reaction. Okay, so we have named reactions associated with these enolate ions. Okay, so the first thing we have is what we call the aldol reaction or the aldol addition reaction. Okay, so what we're going to do is in the aldol reaction, we're going to add an enolate to an aldehyde or a ketone. Okay, and when we do this, it generates an aldehyde or ketone and an alcohol. Okay, so let's go through that step by step. Okay, so if we have our acetaldehyde or ethanol, and we have base, we can turn one of them into an enolate. So it's going to pull a proton off one of these here, and that enolate is, oh, we're not going to pull that one off, sorry. We're going to pull this one off right here. If we pull this proton off because it's acidic, it's an alpha hydrogen, and then we create our enolate here, and it attacks the carbonyl here. So we're forming a new sigma bond from this alpha carbon to the carbonyl carbon. It creates the carbonyl alcohol material. And in this case, it's an aldehyde. It's a hydroxy aldehyde. Do we see how we're using the same material to attack itself? We take the base to deprotonate one equivalent of the aldehyde, generating an enolate. It attacks the other equivalent of the aldehyde to generate a new carbon sigma bond, and it leaves it as the alcohol. So that's if we have an aldehyde. It does the same thing if we have a ketone, because we can, again, remove this alpha hydrogen, which generates our enolate here, which then attacks as a nucleophile to the carbonyl, and this turns into an alcohol. So we end up with our alcohol, and our original ketone is still there. So when we use a ketone, we end up with a ketone, or what we call a beta hydroxy ketone, because the hydroxy's on the beta carbon now. This is still the alpha carbon, and this is now a beta carbon. So we have a beta hydroxy ketone. If we use an aldehyde, we get a beta hydroxy aldehyde. Okay. This is called the Aldol reaction. Okay. So you can think of it as an aldol reaction is an enolate reacting with an aldehyde or a ketone to generate an alcohol. So that's the aldol reaction. Okay. So let's look a little bit deeper into the mechanism here. So the first thing that has to happen, we have to generate the nucleophile. And the way we generate the nucleophile is we take a proton away. Okay. So we have our hydroxy base come in. We find the most acidic proton on our system, which is this alpha hydrogen right here. And then that gives us our enolate ion, which is stabilized by having the charge partially on the oxygen and partially on the chlorine. Now we can react that, partially on the carbon. Now that carbon nucleophile can react with other things. So our carbon nucleophile, that's the next step, sorry. Let's see what's on here. Yes, okay, I have them out of order. All right, so we have our carbon nucleophile now attacking our carbonyl here, generating our tetrahedral intermediate. And notice that this side of the molecule hasn't changed. It's still the aldehyde right here. And then the next thing that happens is it adds a proton because this is our deprotonated alcohol. It adds a proton and we end up with our beta. This is our alpha, this is our beta hydroxy aldehyde. Okay. Now notice that each of these steps is reversible. So that when we think about this, we have to do something to help us drive the reaction to completion. Because each of these steps is reversible. But when you form that carbon-carbon bond, that's actually the least reversible step. And so the reaction kind of goes forward. Okay, so now if you do these at room temperature or not very hot, they will stay as those alpha and beta hydroxy aldehydes or ketones. However, if you heat them up, we can now lose water. It is an acid or base catalyzed dehydration, and we will generate a double bond in conjugation with the carbonyl. And this is called the Aldol Condensation because you're going to lose one equivalent of water. Okay, it's going to condense out of the flask. Okay, so the aldol reaction is reversible, but once you dehydrate it, it is going to drive it to being less reversible. So that it is going to give you very high yields of the dehydration product. And we call these alpha beta unsaturated aldehydes and ketones. Because look, we took away a hydrogen and we took away the OH here. So now we have a double bond. So that is not a saturated hydrocarbon. And it's right next to this carbonyl. So it's an alpha beta unsaturated aldehyde or ketone. So the aldol reaction gives us that beta hydroxy aldehyde or ketone. The aldol condensation gives us an alpha beta unsaturated aldehyde or ketone. Okay. Now, in those two previous reactions, we used the aldehyde that we made the enolate to attack another equivalent of the same kind of aldehyde. Okay. However, you can actually do it where you don't use the same aldehyde in both. In this case, we call it a cross aldol reaction, meaning one thing can make an enolate, the other thing can't make an enolate. Okay, so what does that mean? That means one of your compounds is an aldehyde or ketone with alpha hydrogens. The other compound you have is a carbonyl compound with no alpha hydrogens. All right, so let's look at this. So in this case, we're taking acetone and we're taking formaldehyde. Notice there are no alpha hydrogens because there's no alpha carbons. So we cannot form the enolate from this substrate. However, this has an alpha hydrogen on both sides. So we're going to take one of those off, turn it into the enolate. Once we turn it into the enolate, it'll react with the other carbonyl compound to generate the primary alcohol. Okay, we already have 2 hydrogens on here. We're going to create a new carbon-carbon bond here, and that generates this end is a primary alcohol. So we now have a beta hydroxy ketone, but we know exactly which side was going to be the aldehyde. I'm sorry, which side was going to be the enolate and which carbonyl got attacked preferentially. So we call that a cross Aldol condensation. And usually these are a lot cleaner because only one thing forms the enolate and then it attacks the other thing. So it makes it a nice, cleaner reaction. Okay. So we call that the crossed because you're making the enolate only out of one and then it's attacking something else. Okay, 12, okay, got 15 minutes, all right. Okay, so it's really useful to use. It's a lot less reversible and it's a lot cleaner reaction if you have, you choose your substrate correctly. So the idea is one of your carbonyl compounds should have 0 alpha hydrogens and the other one should have 1 type of alpha hydrogen, and you're guaranteed to have 1 product. So what do I mean by things without alpha hydrogens? Well, think of formaldehyde. There's no alpha carbon, so there's no alpha hydrogen. Here we have an alpha carbon, but there's no hydrogen on it because it's taken up in the benzene ring. Here we have an alpha carbon, but it's part of a ring, and therefore it's not, it has no hydrogens on it. And here we took it and we put 3 methyl groups on there. So it again has no alpha hydrogens. So this would be the thing that gets attacked by the enolate. Okay. Now, what if you have 2 carbonyl compounds hooked together in the same path? Well, you have an opportunity to have an enolate on one side come around and attack the carbonyl on the other side. Okay. However, you have to be careful about that because these types of reactions typically only form 5 and 6 membered rings because those are the most stable rings. It's harder to do 4, 7, or smaller than 5 or larger than 6. So that means you have to pick which alpha hydrogen is going to be the one that forms the most stable product. Okay, and so these are called intramolecular aldols because they're forming. And actually the reactions are really fast because they don't have to diffuse and find the other member. It's just right there all the time. Okay, so we have a choice, right? So we have to pick the one that forms the enolate that gets us a 5 or 6 membered ring, okay? So let's consider this one right here, okay? So we have these alpha hydrogens are equivalent to those alpha hydrogens, right? They're a methyl group next to a carbonyl. So we're only gonna look at one side of that. And these alpha hydrogens are equivalent to those alpha hydrogens because they're next to the carbonyl next to a methyl group. Okay. So if you're convinced that those are equivalent, we're gonna say we're just gonna attack one. So we have a choice of taking the alpha hydrogens off of this carbon, the number 3 carbon, or taking the alpha hydrogens off of the number 1 carbon, okay? It will probably take the hydrogens off either of those carbons. However, only the one that would form, only the enolate that can form the 5 or 6 membered ring will go to product. Okay, so let's look at that and figure out which one it's going to do. Okay, so if we take the enolate and take it off of this hydrogen, this alpha hydrogen here, we're going to end up with our enolate, our nucleophile here, and then it attacks the other carbonyl here, giving us a 5 membered ring. Okay, and it initially gives us this alpha hydroxy ketone, and if it heats up, it loses that and gives us our double bond to give us our 5 membered ring. Okay, okay, you said something about 5-membered rings and 6-membered rings. But let's go ahead and take one off the other side. Let's go ahead and try to deprotonate the ones from this side of the thing. So if we did that, we would create the enolate on the end of the chain, which then would attack the other carbonyl compound, which would give us a 7-membered ring with our alpha hydroxy, our beta hydroxy ketone. And that beta hydroxy ketone will then lose water and generate our alkene. Okay. So, which is the major product? The 5-membered ring or the 7-membered ring? Chat's open. So we're going to form the 5-membered ring preferentially because it forms 5 and 6-membered rings preferred. So that means that even though you have a choice of the red hydrogens and the blue hydrogens, and if you think about it, there are 6 blue hydrogens because of the, these are the same as those, and there's 3 on each of those. And there's 4 of these because there's 2 here and 2 here. Statistically, you think you'd make the 7-membered ring because there's more alpha hydrogens. But no, because the ring is more stable as a 5 or 6-membered ring, it preferentially reacts with the enolate when it removes these alpha hydrogens. Okay, so that's the aldol condensation. Aldol condensation is whenever you have an aldehyde or a ketone, it first generates a beta hydroxyaldehyde or ketone, and then if you heat it up, it turns into an alpha beta unsaturated aldehyde or ketone. Okay. But when we looked at the acidity there, we saw that you could also remove protons that were alpha to esters. That reaction has a different name. We call that the Claisen condensation. So the aldol is aldehydes and ketones only. The Claisen is esters only. Okay, write that down. The Claisen is esters only. Okay. So if the Claisen is with esters only, we have to still have alpha hydrogens. And when we have those alpha hydrogens, we're going to create a beta keto ester. Okay. So when we look at our ester, one side will never have alpha hydrogens because that's the ester portion. So we have one place to take off those alpha hydrogens. It's on the other side. So we're going to take off the hydrogens on here, and it's going to attack another equivalent of the of a different ester. Okay, but why do we end up with a ketone? We need to figure that out. Okay, we end up with a beta keto ester, meaning the ketone is beta to 1 ester. Okay. Why did we end up with this? We ended up with the hydroxy compound last time. Okay, so let's talk about it. Okay, so in this case, we have one requirement is we actually have to use a non-aqueous base, because if we had an aqueous base, it would hydrolyze the ester. We saw that aqueous bases hydrolyze esters in the last chapter. So we have to use a non-aqueous base to do this system. So typically we use an alcohol with an alcohol, the salt of that alcohol, like alkoxide in ethanol, methoxide in ethanol, and you want to use the same alcohol in your solvent as you have on your esters. So that's kind of an important thing. So if you had methyl alcohol, if you have a methyl ester, you want to use methanol. If you have ethyl esters, you want to use ethanol. Okay. So that's kind of important there. So no water, and you use the same alcohol that you have the ester of. Okay. But I still don't know how it works. Okay. So let's talk about that. So the first thing, of course, we have to do is we have to form the enolate. Okay. And we only have one choice of alpha hydrogens because the other side's the ester. And so we form the enolate on that alpha carbon, giving us our nice stabilized, resonance stabilized enolate here. Okay. So now this one can act as a nucleophile, and this one helps stabilize the enolate. Okay. So the next thing that has to happen is we use it as a nucleophile to attack another ester. And when we do that, we end up with our tetrahedral intermediate here. But look, we have something that can leave as a really good leaving group. In fact, we just used this ethoxide to generate our enolate. And if we kick this in and kick this out, we're going to regenerate that ethoxide. So I think that might be the next step. So the next step is to actually do that. We're going to have our electrons come in here, regenerate our carbonyl compound, kick out our ethoxide. Our ethoxide can then go and make a new enolate. And we've generated our beta keto ester. Notice the ester of the enolate is the one that stays intact. The carbonyl on the neutral molecule is the one that ends up having the ketone. Okay. Now, why does it stop there? Why does it do this? Well, it turns out that now that you have two carbonyls on there, that hydrogen is more acidic than when it had just the one carbonyl on there. So what happens is this ethoxide deprotonates that, and it stops as a anion here. Now, this can act as a nucleophile because it's got the negative charge there, but it also is stabilized over two oxygens. You can go either way to stabilize it, and actually it turns out it's less nucleophilic than the smaller molecule because it's a weaker base than the other molecule. So it's stable. It sits there as the salt until the end of the reaction. Then at the end of the reaction, you add acid to protonate that alpha hydrogen, and you end up with your beta keto ester. Do we understand the mechanism here? It's a little bit longer. It's probably one of the longest mechanisms we've done, but each step makes sense. We take a strong base, we take a base to make a stronger base, so it's in equilibrium, and it's mostly on this side because this is the stronger base. But enough of it is there that once you form it, it reacts as a nucleophile, and that's why the reaction progresses forward. Now this also generates this tetrahedral unit, which is less stable than having the enolate. So this is an equilibrium, but it slowly moves to having some of this. Now, once we form a little bit of that, we have another equilibrium reaction of it losing that ethoxide right here. And then the next reaction is the one that drives us home. The next reaction is when it deprotonates our keto ester here, turns it into this weaker base, and that's what's driving us to completion, is the fact that that is the most stable product in the set, and it stays there until we acidify. Okay, questions on that? Okay. Again, the Claisen always happens with esters, and it always gives a beta keto ester out the product. So if we had an intramolecular aldol, is there an intermolecular Claisen? Well, the answer is yes, and we call that the Dieckmann condensation. The Dieckmann condensation is just like the Aldol condensation. We're going to form 5- and 6-member rings, and we're going to end up with a beta keto ester at the end. It's the same mechanism. In this case, we only have a choice of one possible place to take our alpha hydrogens off of, and one possible place for it to react. Okay. So I will stop there since we're right at 12:20. We started at 11. Yeah, that's right, 12:20. So, and we will continue here on Tuesday. I'm going to go ahead and stop recording. If you want to stay back and ask questions, please do. If not, go ahead and run off to your next class. Stop share and stop record.